Hi everyone, so today we're doing lesson 4.5 and 4.6, which is exploring the properties and transformations of exponential functions. So there's a handout on Teams that you should print out and fill in as you watch this video. So we're going to get started. It says on your handout, create a table of values to graph the following functions. So first I just want you to take a look at that function there, f of x equals 2 to the power of x. I just want to point out that the variable is now in the exponent, which is what makes us an exponential function and what makes it different from the functions we've been studying so far. So, looking at the table of values there, I have x values given to me, and then I have a y column, and then I have a first differences column. So, my x values are from -4 up to +4. And I'm just going to plug those into this equation, 2 to the power of x, and see what I get out for y. So if I have 2 to the power of -4, that's the same as 1 over 2 to the power of 4, which equals 1 over 16, which equals 0.0625. If I have 2 to the power of -3, I have 1 over 2 to the power of 3, which is 1 over 8, which is 0.125. 2 to the power of -2 is 1 over 2 squared, which is 1 over 4, which is 0.25. 2 to the power of -1 equals 1 over 2, which is a half. 2 to the power of 0, anything to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4, 2 to the power of 3 is 8, and 2 to the power of 4 is 16. Now, if I look at the first differences here, I have 0.125 minus 0.0625, which is 0.0625. Then I have a quarter minus 0.125 is 0.125. Then I have a half minus a quarter is a quarter. 1 minus a half is a half, 2 minus 1 is 1, 4 minus 2 is 2, 8 minus 4 is 4, and 16 minus 8 is 8. So these are not constant, but do you notice the pattern at all? So the pattern is actually that we're multiplying by 2 each time. And that's important later. Just note that for now. All right, the next table of values is g of x equals 0.5 to the power of x. So we're going to do the same thing with our table of values. All right, so if I plug in -4 for x, I have a half to the power of -4, which is the same as the reciprocal of a half to the power of +4. The reciprocal of half is 2 over 1, or just 2, to the power of 4, which is 16. Now I have a half to the power of -3, so the reciprocal would be 2 to the power of +3 is 8. 1/2 to the power of -2 is the same as the reciprocal, which is 2 to the power of 2, which is 4. 1/2 to the power of -1 would be the same as the reciprocal, which is 2 to the power of 1, which is 2. 1/2 to the power of 0, anything to the power of 0 is 1. 1/2 to the power of 1 equals a half. 1/2 squared equals 1 over 2 squared, which is a quarter, which is 0.25. 1/2 cubed is 1 over 2 cubed, which is 1 over 8, which is 0.125. And 1/2 to the power of 4 is 1 over 2 to the power of 4, which is 1 over 16, which is 0.0625. Now the first difference is here. 8 minus 16 is -8, 4 minus 8 is -4, 2 minus 4 is -2, 1 minus 2 is -1, a half minus 1 is -1/2, a quarter minus a half is -1/4, an eighth minus a quarter is an eighth, and a 16th minus an eighth is 1/16. So again, first differences are not constant, but there's a pattern again. And now we're dividing by 2, which is actually the same as multiplying by 1/2. And you'll also notice that these numbers went in reverse order of the last chart that we did. All right, so now you're going to plot these points on a graph, so the X and Y columns on the graph to the right there, and you can put them both on the same axis and label them. Just maybe pause the video and take a few minutes to do that, and then my graph will be up next. All right, so your graph should look something like this, with this line being 2 to the power of x, and this line being 0.5 to the power of x. Okay. So down below the graph there is a chart, and it says properties of exponential functions. So when I have this function, f of x equals 2 to the power of x, we call this 2 the base, or b. So looking at that chart, I have exponential growth occurs when b is greater than 1. So, for example, y equals 2 to the power of x, 2, the base, is greater than 1, and in the graph here, we saw it went up, it grew. Now, exponential decay happens when b is between 0 and 1, or it's a fraction. It's not a whole, it's not 1, it's part of 1. Okay, so that happened when we had y equals 0.5 to the power of x. We started out big, and then our graph got smaller and smaller as we went on. So that was exponential decay. And then below that, we have a note about first differences. And I sort of already mentioned that, but that note is, though the first differences are not constant, they are related by a pattern of multiplication. All right, and then this is actually moving on to 4.6 now. We're going to talk about transformations. And the transformations that happen to exponential functions are the same transformations that we studied up until this point, but now they're just happening to an exponential function. So I'm transforming the function y equals b to the power of x to become y equals a times b to the power of k, bracket x minus d, and then this is no longer an exponent, plus c. So I have the same a, k, c, and d values that we've talked about this whole time already. So let's just recall, what do they do? So a stretches or compresses vertically. K stretches or compresses horizontally. C shifts vertically, so up and down, by C units. And D shifts horizontally, left or right, by D units. And you need to remember that the original equation is x minus d. So you need to do the opposite sign of D when you're working with D. As usual, that's how we've always learned it, but just a reminder. And also, the order that you do the transformation does matter. You need to do the multiplication first, so the A and K first, and then the addition and subtraction, just like BEDMAS. So this is the order that we do them in. A, K, C, and D. A and K don't matter what order, they can be reversed, and C and D don't matter, but first A and K, and then C and D. All right, over to the second page. So complete the table below to explore how exponential functions are transformed. So there's 4 functions there, and we're going to graph them each individually. So first we'll make the table of values, and then do the graph. So first I have g of x equals 2 to the power of x, 2 to the power of x plus 1. All right, so my table of values, my x values are -4, -1, 0, 1, and 4. And then my y values, I'm just going to plug those x values into the equation. So 2 to the power of -4 plus 1. 2 to the power of -4 is 1 over 2 to the power of 4, which is 1 over 16, plus this 1 equals 1.0625. 2 to the power of -1 plus 1 is the same as 1/2 to the power of 1, plus 1 is 1.5. 2 to the power of 0 plus 1, 2 to the power of 0 is 1, plus 1 is 2. 2 to the power of 1 plus 1 is 2, plus 1 is 3. 2 to the power of 4 plus 1 is 2 to the power of 4 is 16, plus 1 is 17. So now just take a minute to plot these points on your graph. The line that's given there is the parent function, 2 to the power of x, and just draw your line on that same graph just to compare. So pause the video and draw it now, and then my graph will come next. All right, so there's my graph, and that 1 that we had added behind, so 2 to the power of x plus 1, that 1 was a c value. So now below your graph, there's a block that says changes to parent function. So what changed? How was our graph moved from the parent function? So we noticed that all the y values were increased by 1. Or in other words, it was a vertical shift up 1 unit, which makes sense because this was the c value, and c affects the vertical shifts. All right, next one. So now I have h of x equals 2 to the power of x plus 1, where that 1 is now in the exponent, so that would be a d value. Now the table of values, x is -4, -1, 0, 1, and 4, and y is, plug it into the equation, so 2 to the power of -4 plus 1 would be 2 to the power of -3, which would be 1 over 2 to the power of 3, which would be 1/8, which is 0.125. When x is -1, I have 2 to the power of -1 plus 1, which is 2 to the power of 0, which is always 1. When x is 0, I have 2 to the power of 0 plus 1, which is 2 to the power of 1, which is 2. When x is 1, I have 2 to the power of 1 plus 1, which is 2 to the power of 2, which is 4. And when x is 4, I have 2 to the power of 4 plus 1, which is 2 to the power of 5, which is 32. Okay, so pause the video, take a minute to draw your graph. All right, so your graph should look something like this. And now the changes to this graph, so you'll notice that all the x values were decreased by 1. So it's kind of hard to read. All x values decreased by 1, or a horizontal shift left 1 unit, which makes sense because that plus 1 was the d value, and in the original equation, it's x minus d. So now if d is negative 1, that will become x plus 1, which is what it was. So d was actually negative 1, which is why we moved left. All right, the next one is p of x equals negative 3 times 2 to the power of x. So only the 2 is to the power of x. Let's be clear on that. So this is now our a value that we're using. So my table of values, I have the same numbers, negative 4, negative 1, 0, 1, and 4. Plug those into the equation. So negative 3 times 2 to the power of negative 4 equals negative 3 times 1 over 2 to the power of 4 equals negative 3 times 1 over 16 equals negative 3 over 16, which is negative 0.1875. When x is negative 1, I have negative 3 times 2 to the power of negative 1, which is negative 3 times 1 over 2, which is negative 3 over 2, which is negative 1.5. When x is 0, I have negative 3 times 2 to the power of 0, which is negative 3 times 1, which is negative 3. When x is 1, I have negative 3 times 2 to the power of 1, which is negative 3 times 2, which is negative 6. And when x is 4, I have negative 3 times 2 to the power of 4, which is negative 3 times 16, which is negative 48. So take a minute to plot those, pause the video, and mine will be up shortly. Okay, so here's the graph. So for this one here, you'll notice that a value was negative, so the graph has been reflected. And you can see my explanation here. So all the y values were multiplied by negative 3. So we can say a vertical stretch by a factor of 3 and a reflection over the x-axis. All right, moving on to the last one. So the last one is q of x equals 2 to the power of 2x. And this here is our k value. So the table of values, negative 4, negative 1, 0, 1, 4. Plug those values into the equation. 2 to the power of 2 times negative 4 equals 2 to the power of negative 8 equals 1 over 2 to the power of 8 equals 1 over 256, which is a very small number, so I'm just going to leave it like that. 2 to the power of 2 times negative 1 equals 2 to the power of negative 2 equals 1 over 2 to the power of 2 equals 1 over 4 equals 0.25. 2 to the power of 2 times 0 is 2 to the power of 0, which is 1. 2 to the power of 2 times 1 is 2 to the power of 2, which is 4. And 2 to the power of 2 times 4 is 2 to the power of 8, which is 256. All right, so pause again and draw your graph. All right, so your graph should look something like this. So it goes up very steeply and changes to the parent graph. So you'll notice that all the x values are divided by 2, which is the same as being multiplied by 1/2. So we have a horizontal compression by a factor of 1/2. All right, so that's it for this lesson. Let me know if you have any questions, and I hope you can figure it out. Feel free to rewatch the video, pause it, and please let me know if you need help. Have a good day.